Welcome to Chapter 2 of Geometry. This is Section 1, Lesson 1, Patterns and Inductive Reasoning. Our objective for today is to use inductive reasoning to make conjectures. So the first thing I want you to think about is folding a piece of paper in half. When you fold a piece of paper in half, and then when you unfold it, it's divided into two rectangles. When you fold it in half, refold it, and then fold it in half again, now there are four rectangles. And I want you to think about, okay, if you did this 8 times, how many rectangles would there be on your paper? And if you want to get out a piece of paper and see if you can find a pattern, but pause the video here and try and do that. As I did this, I started to notice a pattern. With one fold, there were 2 rectangles. With 2 folds, there were 4 rectangles. With 3 folds, there were there were 8 rectangles. With 4 folds, there were 16 rectangles. And then I noticed, okay, well, each one of these is a power of 2. We have 2 to the first, 2 to the second, 2 to the third, 2 to the fourth. And so then I noticed, well, if there's 8 folds, it's probably going to be 2 to the 8th. And 2 to the 8th, I do that right now, 2 to the 8th power is 256. There will be 256 rectangles if you can get your piece of paper to be folded that many times. I couldn't get my paper folded that many times. And so we can start to think inductively by starting to notice patterns and then continuing those patterns on. Alright, and so some of the things we're going to be talking about, we're going to be talking about inductive reasoning, and what it is, it's based on the patterns you observe, just like in that previous problem. And you can observe patterns in some number sequence and some sequences of geometric figures to discover these relationships. So if you look at these problems right here, we're looking for a pattern so that we can then predict the next 2 terms in each sequence. And so if I look at this, okay, from 3, 9, 27, 81, well, I'm adding 6. And then I'm adding 18. And, those don't really seem to be like that good of a pattern, so I'm going to try it again. Alright, let's look at a different one, maybe multiplying. Well, if 3 times 3 is 9, 9 times 3 is 27, 27 times 3 is 81, and so that pattern seems to be working, so I would assume that it would then work for the rest of them, and so we can also think about these as powers of 3. Well, it's 3 to the first power. 3 to the second power, 3 to the third power, 3 to the fourth power. And if we continue on this pattern, we get 3 to the fifth power, which is 243. And we get 3 to the sixth power, which is 729. And that helps us that goes along with the pattern that we found. And so now if we look at the drawings, with the circles with a geometric shape inscribed in them down here. We've got a circle with a triangle in it. The triangle, I notice, has 3 sides. Then we have a circle with a square inscribed that has 4 sides. Then we have a pentagon inscribed that has 5 sides. So my guess then is the next one we're going to have is a hexagon. We'll see if I can draw that nicely. If we have a hexagon, it's going to go like that, that. Nope. Drawing an octagon instead of a hexagon. Let's try that again. We're going to then get a hexagon. There we go. Now you'll start to learn that my drawing skills are very subpar. So this would be the next drawing, a hexagon, which has 6 sides, and then we're going to have a heptagon, which is 7 sides. So 1, 2, 3, 4, 5, 6, 7, and that would be inscribed in that circle as well. Alright, so then you start to see those patterns. So what I'm going to have you do now is pause the video here and see if you can find the next 2 terms in these sequences. And now you can kind of see my patterns. I notice the first one's going down by 5 each time, so my next 2 terms are going to be 25 and 20. And then I notice in the one below, each time they're inscribing another rectangle, and so we get this little extra one in the middle there, and then we get another extra one in the middle there. All right. And so some things we're going to talk about are conjectures. And so a conjecture is a conclusion you reach using the inductive reasoning. Now, if you want to find the 100th term of a sequence, you'd rather find a pattern and make a conjecture instead of finding all the first 100 terms. And so we use the inductive reasoning to come up with a pattern, and then we make a conjecture. And so if you look at these circles down here, here we have the first term in our pattern. All right, and it has one line and two regions. We look at the next circle, it has two lines and four regions. We look at the next one, it has three lines and six regions. And I start to look at that and I notice a pattern. Each time it's taking the number of lines and it's multiplying it by 2 to get the regions. Multiplying it by 2. Multiplying it by 2. And so if I had, instead of having to draw this out 20 times, I can think about, okay, well, if I had 20 diameters, it's probably going to be 20 lines then, and it's going to be 20 times 2, which would be 40 regions. And so we made that conjecture, we noticed a pattern, and then we found a conjecture, and then we found our 20th term in our pattern. And so now you're going to do the same thing down here. Pause the video here and take the time to do this problem. Alright, and so what I noticed, I went through and I just labeled them each as the number term they were. So R was the first term, W was the second, B was the third, and then B once again was the sixth, which means B is probably going to be the ninth, and it's probably going to be the 12th. And through that I know that B is always going to be in a term number that's a multiple of 3. And I know that 21 is a multiple of 3, which means that the 21st term would be B. And so we can use, once again, we use inductive reasoning to come up with a pattern, and then we made a conjecture for the last term. And so some other things that we know is that reasonable conjectures must be based on a pattern that you're observing. And so if we look at this sequence here, it's 1, 3. And that's all they give us in this sequence. And so in that situation, it's hard to, there's not really a reasonable conjecture you can make through that. You don't have enough information. Usually you need at least, I would say at least 3 terms to make a reasonable conjecture. Because for all you know, like it could be the powers of 3, 3 to the 0, 3 to the first, and 3 to the second. Or it could be increasing by 2. And so you've got a lot of different options for patterns, and so usually you need at least 3 terms. And so if you look at this next pattern, 3, 8, 11, well, we can start to make a reasonable conjecture about this one. Each time it's going, here it's going up by 5, here it's going up by 3. Well, maybe we can, maybe we can't, but we have a little bit more information. If they gave us maybe a 4th term in this pattern, we could start to see if maybe it's a repeating pattern where it's increasing by 5 and then increasing by 3. But there's really not enough information in that one either. And so a lot of times we need to start collecting some information to make a conjecture. So if you're going to make a conjecture about the sum of the first 30 even numbers, well, we're going to start off and we're going to just start to write down some of these. So if we're dealing with our first term, that's just going to be a 2. 2 plus itself is 2. And then our second one, we're going to have 2 plus 4, and that's going to give us 6. And then we're going to have our third term, 2 plus 4 plus 6, and that's going to give us 12. And then in our fourth one, we're going to have 2 plus 4 plus 6 plus 8, and that's going to give us 20. And so if I look at these now, okay, let's see if there's a pattern in the sum. Well, this one is 1 times 2. And this one is 2 times 3. And here I have 3 times 4. And then 4 times 5. And so if my guess is the next one's going to be 5 times 6, and then 6 times 7, etc. And so for the 30th term, it's going to be that number term, which will be 30 times whatever the number of the next term is going to be, 31. 30 times 31 gives me 930. And so there we collected information so we can make an conjecture that the sum of the first 30 even numbers is going to be 930. So now what you're going to do is you're going to do the similar process, and you're going to make a conjecture about the sum of the first 30 odd numbers. So I'd start doing the exact same thing we did. Start writing down information, seeing what you can collect. So pause the video here and do that. Alright, and so now you can kind of see my patterns. I noticed that each time the sum was the number term squared. So the first one was 1 squared, 2 squared, 3 squared, 4 squared, 5 squared. So if we continue this pattern on down, we're going to get the sum of the first 30 odd numbers to be 30 squared, which is 900. Alright, and so here we have now we're going to start making some predictions once again. And so here we have a graphic, and it says the sales of backpacks at a nationwide company decreased over a period of 6 consecutive months. What conjecture can you make about the number of backpacks this company will sell in May? And so if we look at these backpacks, it kind of looks like it's pretty close to making a line through there. And if I look at that, well, each month it seems to be going down by 500. And if it goes down by 500 each month, that would mean that in May, it's going to be about 8,000. And so there, we looked for a pattern, we saw the pattern, and then we made a conjecture that for May, they're going to have about 8,000 sales for backpacks. So what I'm going to have you do now is you're going to use that same graphic to see if you can make a conjecture about backpack sales in June. So pause the video here and make a conjecture. For A, I would say that for June, if we're going to follow the similar pattern, backpack sales are going to be about 7,500 if it continues along that line. And so the next question they ask is it reasonable to use this graph to make a conjecture about sales in August? And I would say that no. And the reason why is because in the U.S., and if long as this is a graphic about the U.S., schools get back in session in August and September. And so in August and September, if you walk into any of your local Targets, Walmarts, any store like that, there are backpacks everywhere that they are trying to sell. And so in August, I would assume that the sales are going to increase dramatically from the rest of this pattern. And so a lot of times we know certain things about a variable or about a situation that maybe this pattern is not going to continue down, where we know, okay, there are going to be times where it's going to jump back up. All right, so some stuff that we've done, we follow established patterns to make our conjectures, but we may be wrong. And so that's one thing that we need to always keep in mind is just because there seems to be a pattern does not mean that we are right. And so you need to always make sure to test your conjecture several times. If you find even one example where it does not work, then your example is not true. And we call that example a counterexample. All right, and so anytime you find a counterexample, then your conjecture is not true, it's false. And so here we got some situations, and let's see if we can find some counterexamples. It says if the name of a month starts with the letter J, it is a summer month. Well, okay, first off I'm like, oh yeah, June, July, those are both summer months, but I'm like, wait, what about January? The coldest month of the year. That's not a summer month, so we know it's false. You can connect any 3 points to form a triangle. So I started thinking, oh, here I have 3 points. Oh yeah, those make a triangle. Oh, here I've got 3 more points. Those ones make a line. I can't make a triangle out of those 3. All right. When you multiply a number by 2, the product is greater than the original number. So I start to do some problems. Oh, 2 times 4. That's going to be 8. Oh, 2 times 5, that's 10. So both of those work. But what if I do 2 times 1/2? That's 1/4. 1/4 is smaller than 1/2. Here's my counterexample. So I know that the conjecture is false. So what you're going to do now, this is your last problem. You're going to come up with 3 counterexamples for each one of these conjectures. So pause the video now and do that. Alright, here are my examples. In my first one, I just went online and I actually got a picture. These are some Gerber daisies. So these are not roses, and they are red. My next drawing, let me see if I can try and explain this a little bit. I have 3 points, 1, 2, 3, and if they form a line, then there are infinite number of planes that can go through them. Like here's a vertical plane that goes through them, here's a horizontal one that goes through them, and there's even more. And then when you multiply a number by 3, the product is divisible by 6. Well, 3 times 3 is 9, and 9 is not evenly divisible by 6. So there we have 3 counterexamples for all 3 of those conjectures. If you have different counterexamples, but they still prove the same point, then that was exactly what we were trying to get at. So this is the end of Lesson 1 of Chapter 2 of Geometry.